So two of the common functions that you run into in a lot of programming languages is you have a ITOA and an IoT. And all it is integer to ASCII and ASCII to integer. They just shorten it. And you may not think about that, but how do we actually make an integer to ASCII? How do we get a computer to say, look at this number and get to print out the actual digits? There's two ways of doing it primarily. There's one way where you're using powers of 10, and there's one way where you're doing essentially a long division with the computer. And I think that both of them are important and they both have their usages. One of them is easier to scale up. If you do the long division one, then you can do it over a very, very large number because you only need to look at smaller parts of the number. But with the power one, if we do the powers of 10, then you need to know how big the number is going to be before you actually start. And so for this one, let's just pretend that our number is always going to fit into a 32-bit number. And if we think about how many digits a 32-bit number can be, the largest it can be is 10 digits, which is actually the same for signed and unsigned, but we're going to work on unsigned right now. And so what we're going to do essentially is we're going to take 10 and 10 to the ninth, and we're going to see how many times 10 to the ninth goes into a number. And then we'll take 10 to the 8th, and then we'll see how many 10 to the 8th goes into the number, and we'll take 10 to the 7 and see how many that time goes into the number, so on and so on and so forth. And so you can hear where the loop is going to be already in this. And because I don't want to have a bunch of zeros at the beginning of the number when we output it, we're going to actually do two loops. We're going to do one loop that tries to figure out if it's higher than that so we don't get leading zeros, and then do the number itself. So let's break this down a little bit. The first thing that we should do is load the address of the number where we're going to store our number at. And so let's put this in register 4. And then before we get too far in here, and then the next thing that we need to load is obviously the number that we need. And we've used the EQU directive to define base number as the number that we're going to use. And so we're going to use LDR R5 and set that equal to base number. And so you may think, why load register? Because this number doesn't fit in the immediate for a move instruction. When this program is compiled, what it's actually going to do is going to put this number into memory, and it's not going to treat it as an immediate. And so it will actually use the LDR, the load register, and it'll compute the address that this number is stored without us doing anything. And it'll load that number into the register. And so that's part of the reason why we have these pseudo instructions, is because every pseudo instruction, what it's actually doing is it's putting a value in memory, or it's trying to figure out where something is in memory. And then when it gets assembled, it'll put that address in this spot for us. And in that way, it's doing the same thing when we read with the LDR and then put the register number in brackets to get to that address. It's just that with this, we don't have to know where that address is going to be in memory for the data that we're looking for. It'll automatically do all that calculations for us. So the next thing that we need is first of all, we should come up here and put register 5, and we'll just put a note that says number to process. And so the first thing that we need to do is we need to load our maximum power of 10, and we'll go move. We'll put this in R7 for no particular reason. And then we're going to try and find the start of the number, because we don't, so if we have the number 5 and our first power of 10 is 10 to the 9th, what's going to happen is that the first time it goes through, it's going to say, well, the first one's 0 because it doesn't fit into it. And so we'll have 0, 0, 0, 0, or 0, 0, 0, 0, 0, 0, 0, 0, 5. And so I don't want that. What I want to do is I just want to have to say 5. If it's 5, I just want to say 5. And so let's do a loop here that tries to find the starting value that we can put in here. The first step that we need to do is we need to take 10 to the power of 9. So as you think about that, there is no power operation. And so what we actually need to do is we need to write the power operation for this. So let's make this a macro. And what we need to know for this is we need to use the base, right? We need to know what number is the base, and we need to know the power, and then we need something that will keep a total. Because what we're going to have to do is we're going to have to multiply it over and over and over again. So when we try to find the power of something, so if we take 4 to the power of 4, we'll multiply 4 by 4, and then multiply that by 4, and then multiply that by 4. And so 4 times 4 is 16. 16 times 4 is 64, and then 64 times 4 is 256. Correct. And so those are the things that we're going to have to store. So let's make this macro. We do that by putting the macro directive, which is .macro. And then the parameters that we need are the name of the macro, and then the arguments for the macro itself. We need the base number, and we need what the exponent is going to be. And so this is one of those times where it's going to be beneficial to use the first couple of registers because we're going to use them over and over again. And since our other registers that we use in the program are after register 3, we can do whatever we want in these registers and not worry about messing up anything else that's going on. So the first thing that we should do is load the base number. And so we'll move into register 0, the base. So here, we'll just make a note that R0 is going to be the base. And then let's put the exponent in the next register. We have to do this because the multiplication operations, multiplication instructions, require you to use 2 registers. You can't do register times intermediate or intermediate times intermediate. If you're using the multiplication, then it has to be register and register. The first thing that we're going to do before we actually write the loop that's going to multiply and multiply and multiply is that there's one funny thing about taking things to the power of something else. It's that if you take it to the power of 0, then the answer is 1. I still don't understand why that is. I think it was explained to me once in math in high school. And it had such a lasting impression on me that I don't know. But I do know that if we take something to the exponent of 0, the answer is 1. If we tried doing this, we could get 0, we could get an infinite loop. So we need to make sure that we have something that looks at this case. And so we're going to compare the exponent to 0. And if we do, then in the result, so move equal, we're going to put into the result, which is going to be R2. We're just going to put 1. And then we're going to branch somewhere if it's equal as well. I don't know where it's going to be yet. So we'll just leave that label empty for now. But if we don't have a 0 exponent, the first thing that we need to do is we actually need to move the base into the total, so that when we multiply the total by the base again, we don't get 0, because right now it'd be 0. So we'll move the base into the total. So R2, R0. And then what we're going to do is, because we moved it over, we've already used one of the exponents up. Even though we haven't multiplied anything, it's like that first one, the base, we take one exponent off. So out of the number of the power, we'll subtract 1. So now we should be set up to actually do the loop of creating this exponent. So let's put a label here. And we'll say that 1 is the main loop. And so what we need to do is, first of all, we need to figure out if we're at the end of our comparisons. So if our exponent is 0, so we're going to compare the exponent, which is R1, to 0, we're done. And so what I used here is BLE, and you can just put equals. Many times, though, when I work with loops, I always put 0 or less than, or equal or less than, or greater than or equal than. And part of it is because I'm unsure sometimes, like at first what I'm testing for, but more so is that if there's some kind of unexpected behavior, we don't want it to run forever. I would rather have it return a wrong answer so I know what it's thinking, as opposed to just loop and never really know what it was trying to do. And so you could put branch if equal here, but you could also put BLE, which is branch if less than or equal. And then if we're done, we'll go to label 2, somewhere in the front of us. And so we'll put here label 2 is the exit routine. And now we can put something here with the branch equal here. We can put 2f up there as well. Now, if we still have exponents that we can process, then we want to multiply the base by the total, or the total by the base. And so we want to store it in R2, and then we want to take the base, which is R0, and multiply it by the total. And so if you think about this, so if we have 10 to the third, The first 10 is 10, and that's what we stored before the loop. The second one would be 10 times 10, which is 100. And then the third would be 10 times 100, which is 1,000. And so every time we multiply the base by the total in order to get the next exponent of values. So after we multiply it, what we need to do is take 1 from the exponent. So really what's happening is the exponent is acting as a loop counter in this scenario because the exponent number never actually gets factored into the mathematical expression. It's just a count of how many times this mathematical expression happens. And so we're going to subtract 1 from R1, which is the power. And then we're going to branch to the beginning of the loop. 1 and then B because it's back. And then label 2. What we're going to do is we have a total now, and it's living in register 2. But generally, when you have a function like this, the return value is going to be in register 0. And so let's do that. And so the last thing that we'll do in this macro is that we'll move the value from R2 where we were storing it and put it in R0. And then that should be the end of our macro. And so if you think about it, again, this is very valuable to actually run it through your head. If we have 10 to the 0 power, what's going to happen in 33 is you're going to load the 10, load the 0. 35, you're going to compare the exponent to 0 and say, oh, we have 0. And so in 36, we're going to put 1 into the total. 37, we're just going to go to the ending routine, and it's going to move the total to R0. Done. If we have 10 to the 2, 10 to the second, it's going to load the 10 and the 2. It's going to compare it to 0. 2 is not 0, so keep going. Down to 38. At 38, it'll copy 10 into the total, and then we're going to have 10, and our exponent's going to get decremented by 1. And so we get to 41. Our exponent is still 1, and so we won't branch to the exit routine. We're going to move our multiply our total by the base, so 10 times 10, which is 100, and then take 1 from the exponent. And now their exponent is 0. Then we're going to branch back up to the 1 label. That we have to use a local label because it's a macro. We're going to compare 0 to 0, and it's 0. So we're going to branch to 2f, this 2 label forward. We're going to move the result, which is now 100, to R0. And so that looks like it'll work just fine for us here. So now that we have a power routine, let's actually use it. So to find the start, the first thing that we're going to do is try taking the power of 10 to our current exponent. And right now our current exponent is in R7. And so because we're trying to find a number that will allow us to not have zeros at the beginning of our number, we want to check if this base of 10 is greater than or less than the number we're going to process. If the base of 10 that we have is less than the number we want to process, then we're fine. Then we know right now that everything will be fine. We won't have a 0 because we're going to have to multiply by something to create a number that we can subtract from that one. But if this 10 to the exponent is greater than the number that we have, then we need to take the next base of 10 down. And so what we can do is we're going to move into, actually, let's do this first. since we put this power macro up here, let's take our registers here. And let's bring this down so that we can actually see it on the same screen. Like that. And so what we're going to do is we're going to move this result that we got from our power of 10. Let's put it in R6. Into R6 from R0 because our power macro returned it to R0. And we're going to compare R6 to the number that we want to process. So we're going to compare R6 to R5. R5. And so now if it's greater than, we want to do the loop again. But if it's less than, we want to jump and actually do all the writing. But what if it's equal to? Do we take the next base of 10 down if it's equal, or do we start trying to process the number if it's equal? If it's equal, then we need to process the number. Because if not, then we're going to have 10 as our first result, because one less base of 10 will go into that number 10 times, and then we have 2 digits, and then we have an issue. And so what we want to do is we want to branch if it's less than or equal to the next section. And we'll call the main loop, the main thing that we do. Let's try find digit. If it's not, then we need to take one off the exponent and then try it again. So we're going to subtract from R7, 1. And then go back to find start. Let's put our find digit. Oh, find digit label. And so let's think about this. So if we have the number 500, we do 10 to the 9th, it's too large. So we subtract 1 from the exponent. We do 10 to 8, it's too large still. We go to the next exponent, 10 to the 7, 10 to the 6, 10 to the 5, 10 to the 4. 10 to the 3 will give us 1,000, which is greater than 500 still. And then we go 10 to the 2. And so we compare 100 to 500, and 100 is less than 500. And so we do that comparison in 59. In line 60, we would branch if less than or equal. 100 is less than 500. And then we'll start processing the number and saving the digits. So how is this going to work? So what we're going to do is we're going to take our current power of 10. We're going to subtract it from the number. And if the result of that makes the number less than the power of 10, then we know to keep going. And so let's use the example we were just talking about. If we have 500, we subtract 100, and we get 400. Is 400 still greater than 100? Yes. And so we'll subtract it again. And we have 300. Is 300 still greater than 100? Yes. So we'll subtract that base again. We'll get 200. Is 200 less than 100? No. So we'll do it again. Is 100 less than 100? No. So we'll subtract 100 again. And then the number of times that we can subtract this while the number that we're processing is not less than the power of 10 will be the digit that will be in this spot. So since we had to do it 5 times, it would be a 5 in that 10 spot. So in code, what we want to do is we first want to compare the number that we're processing, the number that we keep subtracting from, which is R5, and we want to compare it to the current power of 10, which is an R6. And if it's less than, we're going to go somewhere. For now, let's just call this write, because we're going to write it to memory. And put the write label down here. We'll deal with that in a second. And if it's not less than, if it's greater than or equal, what we need to do is increment a counter. And so let's use R8 for a counter. Say R8 for and then again, I like just initializing this up here. It just makes me feel a little bit better when I go to bed at night. R8 we'll do 0. And again, this sometimes will get optimized out as a no operation because your register should be 0 when it gets loaded. But it makes me feel a little bit better at night. And so if it's not, we're going to add 1 to the result to this loop counter. R8, we're going to store it in R8. So we're going to store in R8, adding R8 and 1. And we're going to subtract the base of 10 that we're working with from the number we're processing and store it back in the number that we're processing, which is R5. And then subtract the current base of 10 in R6. After that, we need to go back to our find digit. So we're going to go unconditional branch to find digit. So for our instance for 500, we're going to go 500, no, add 1 to our counter. 400, no, add 1 to our counter. 300, no, add 1 to our counter. 200, no, add 1 to our counter. 100, no, add it to the counter because 100 is equal and not less than. And so our counter is 5. And so when we compare it now, our number to process is 0. And so 100 is greater than 0, obviously. And so then we'll get to write it. And then we need to write 5 somehow. There's 2 ways of doing this. One is we can load the ASCII characters 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 into memory, and then just read the character that is base in memory plus the number that we got in the loop, and then store it. The easier way, or I think what is easier, is just taking the ASCII of 0 and adding our loop counter to it. And so we'll go add the loop counter, which is R8, to the value of the ASCII 0. And that'll give us our char code. Because if it's 0, 0 plus the value of 0 is going to be the value of 0. If we have 2, 0 plus the ASCII value of 0 plus 2 will give us 2 after that, which will be 2. And so this way we create the ASCII value just kind of magically. And then we'll store this into the output. And then increment the output. And then what we need to do is we need to get ready for the next loop because we've done everything that we need to do for this one. And so we need to decrement the 10's exponent. So we're going to subtract 1 from R7. And then we want to compare this to 0, because if it's less than 0, then we're done. Oh. So we're going to say branch if less than, and we'll just call the exit routine exit because it's a descriptive label. But if it's not 0, what we need to do is we need to go through the power again and set up the next power of 10 so that we can subtract it in a loop, so on and so forth. So we'll use our power macro again. Our base is 10, and then our exponent is going to be whatever is in R7. And then what we're going to do is move our result into R6 again, because it's going to return the result in R0, but we don't want it there. We want it in R6. And then what we need to do is reset the loop counter that keeps track of how many times we subtract in order to get the next digit. And that was in R8. And then we need to go back all the way up to find digit. So we'll do an unconditional branch to find digit. So by the time that we get to the exit, we went through this process multiple times. If we had the 500, let's do 512. And so we do the 500 like we did, then we have 12 left. So the next time that we do it, we have 10, and 10 is 10, so it goes through it once, the find digit loop once, and then we have 2, and that'll be 10 to the 0, so we have 1 and then 2, because we subtract 1 twice, and then we have our 512 ASCII stored into memory. So all we need to do now is actually write it out, actually like output it. Eventually what we're going to do is we're going to convert this into something that's more modular that we can use in different situations. But since this is just the program right now, let's actually set up our write call and everything. In the output string, you can see that I filled 11 bytes. I reserved 11 bytes, but we only need 10 digits. And the reason I did that is for the line ending. And so what we can do is let's just put in R8, because we're done with that, the line ending character again. And then we're going to store this into the output string using store byte. R4. And then we don't need to increment it because it's the last character. And then we should just be able to write this and be great. Because we don't know how many digits this is going to be, what we could have done is filled it for 12 bytes and then been guaranteed a null character at the end and just use our null right again. But what else we can do is, because we know that it's always going to be 11 characters and it's never going to be more than that, we don't really need to use the null right. And the benefit is that if you remember our null right macro, we have a loop in there that actually searches character by character until we find a null character. But if we just set up the write call to write 11 bytes, then we don't have to use that loop. And so what happens if we write a byte that's 0 when into standard out? It just doesn't show up. And so all these bytes that we didn't use, by making sure that we're not putting any leading zeros, they'll just be written as null characters, and in standard out they look like nothing. So let's just use our write call, and let's use a length of 11. And so if you've forgotten, our supervisor call number is 4 for write. And then our first parameter is the file descriptor, and 1 is the special first standard out. The second parameter is the address that we want to read from to write to standard out. And so we're going to put that in R1, and it's out str. And then the last thing that we need is the length. And we said that we're just going to make that 11. And then we're going to execute that, or issue the software interrupt by svc 0. And then all we have to do is exit the program. Into R7, we're going to put 1 for the exit. And then the only parameter that we have is the error code, and we'll put that in register 0, which is signifying no error. And then svc 0. And I think that we should be fine with this. So let's try running this. What I've done is I've taken the make file from the last one, and I just moved it over into this one. Because it's only the main file, we don't even have to touch this. We just use the same make file that we did last time. We can issue the command make, and it runs our commands for us, so we don't have to worry about it. And hopefully when we run this, we should get our number, but as ASCII instead of integers. So 209,867,295. And so that's correct. And so again, eventually we're going to take this integer to ASCII and make it more modular so that we can use it throughout all of these math exercises, because everything that we do is going to be converting these integers to ASCII so that we can verify that it did it correctly. But for now, there was your first integer to ASCII implementation.